So, well, I'm not positive. Oh, halfway through, yeah. Make sure that after a half an hour or so you holler at me and I'll break it into chunks so it's a little bit easier. Okay. Thank you, Julia. So we're going to dip our toes into Chapter 5 here for a little bit and talk about trigonometric identities and some trigonometric proof. Oh no, it's the P word. No, proof won't be, it's not that bad. It's not like geometry proof. Okay, so nobody have a panic attack on me. So we're going to start with some basic identities. So some of them we probably already know. So for example, cosecant is the same as, does anybody remember this? When you found the value for like cosecant of 60 degrees, what did you do? 1 over sine. Exactly right. And you guys have talked about secant. When you find the value for secant, you did 1 over cosine. And now, kind of trivially, we can take this first identity, and if we do the reciprocal of both sides, you have like 1 over cosecant x is equal to sine x, or you could just write it sine x is 1 over cosecant x. And this is kind of the way that typically we'd write it. And if we do the same thing to the other one, we get cosine x is equal to 1 over secant x. So these are the 4 basic trig identities, but I would wager that there were some more that you knew already. The next class of identities I want to talk about are the quotient identities. Oops, not indentities. Identities. And there's, oh, bugger, there were 2 more on here that I wanted to put. I lied about that. Good thing I used a eraser. You guys also found the values for cotangent, right? How did you do that? 1 over tangent. And similarly, we can say that tangent is then 1 over cotangent. Now, a common piece of vocabulary that that we use is we call these guys like reciprocal functions, like secant or cosecant and sine are reciprocal functions. Secant and cosine are reciprocal functions, and then cotangent and tangent are reciprocal functions. So just as a piece of vocab there. Now I'm ready for the other 2. We also have some quotient identities. There are 2 of those that we'll talk about. And there's not 4 of these, there were 6. Dummy. So when you're first introduced to tangent, what did we say that tangent was? Right, and then when we translated that onto the unit circle, tangent becomes sine over cosine. And then if we look at the above, we have that cotangent is the reciprocal of tangent, right? So I can say cotangent then is the reciprocal of sine over cosine, which is just cosine over sine. And all these things that I'm saying to you are on the sheet that Tommy passed out to you guys, right? So again, if you miss one of them or whatever, you'll notice that on the sheet there, the top is exactly what we've done so far. So these ones I'm going to just kind of present without real proof because you've seen these before. And I assume with Ms. Codson, she kind of derived why these identities are, or why these are existing. What I want to do now is to introduce the Pythagorean identities. And the first one is sine squared plus cosine squared equals 1. And just as a little aside, when we, yes? Can we circle back to that in a minute? Okay. You just caught me in the middle of this thing. That's okay. As a little bit of an aside, when we write sine squared like this, where the squared is here, this doesn't really make a whole lot of sense, although this is the convention, the way we typically write this, because it's be like the same thing as saying like square root squared, which again doesn't make a lot of sense unless you have something inside of it. But what we really mean by this is that, but for the purposes of like not having to write down a million extra parentheses, we're going to write sine x squared as sine squared x. And worth noting that this is not the same thing as this. Okay, so those three things, this is the same. This is not the same. Just so everybody's clear. And Gabby, I'll circle back to yours here in a moment. But I want to get this taken care of first. We're going to prove this identity. Dun, 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 dun. So, if we go back to the unit circle, what's that? If we go back to the unit circle here, if I pick some point on this unit circle, what is its x-coordinate? It is cosine theta, correct? And what is its y-coordinate? Sine theta, right? So if I draw in this right triangle, what is my length of this side? It is not 1. It's not a radius for the unit circle. It is cosine theta, right? Because we've gone cosine theta over And then to go up, how far have we gone? Sine theta, right? And the hypotenuse of this triangle, now here comes the question you guys have all been trying to answer already, is 1. Why is that 1? That's a radius of a unit circle. Everybody okay? So since it's a right triangle, what can we use? Yeah, the Pythagorean theorem. We get sine squared plus cosine squared equals 1 squared, which is just sine squared theta plus cosine squared theta equals 1. And we're done. Party time. Circling back to Gabby's question, I'm going to just scroll back up. It is possible to also write these expressions in terms of secants and cosecants. So to do that, I'm going to say that, well, using this identity, that sine x is equal to 1 over cosine x, or cosecant x. And then using this identity, that cosine x is 1 over secant x. And then if this is really a division of fractions problem, right? I have 1 over cosecant divided by 1 over secant. And you remember dividing fractions, that's as easy as pi. You flip the bottom and multiply. And that gives me secant over cosecant, which I think is also what's on the sheet. Okay with that? And that's what's on there, right? I don't have the sheet in front of me. Yes. And similarly for cotangent, you can see kind of how this is going to go. I can write it as 1 over secant divided by 1 over cosecant, which is just cosecant over secant. Okay with that, Gabby? Okay, so the dividing fractions thing is what's getting that flipping in there that you were like, why is it flipped to what I would thought? That's what's going on. Okay. So that's Pythagorean identity number 1. There's actually, we're going to have 3 of these. So the next one I'm going to get by taking sine squared theta plus, well, I guess we use x's, huh? What's on our sheet? Are they thetas on our sheet? All right, I guess I'll just switch back to thetas then. Everybody's okay that x and theta, they're just variable names, whatever, they mean the same thing. Now they can't be different inside of the same line, right? Like sine squared theta plus cosine squared x doesn't necessarily equal 1, because those are different variable names now, but you can change the name to whatever you want. Okay, so if we start with this, what I'm going to do is I'm going to divide both sides of this equation by sine squared. we're coming up with a new identity. So we're just going to start with one that we know and manipulate it to get a new identity. Right? And there's three things we have the choice to divide by: sine squared, cosine squared, and 1. Well, it's silly to divide by 1. You're not really doing anything. But if I divide both sides by sine squared, I get 1 plus, what's cosine squared over sine squared? Well, it's cosine over sine. Close. Cotangent. So cosine squared over sine squared is cotangent squared. And what's 1 over sine squared going to be? Well, 1 over sine is cosecant. So 1 over sine squared is cosecant squared. So that gives us our second Pythagorean identity. And similarly, if I start with that first Pythagorean identity, but this time instead of dividing both sides by sine squared, I divide both sides by cosine squared, I'm going to get yet another Pythagorean identity. What is sine squared over cosine squared going to be? Well, sine over cosine is tangent. So sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. And that's our third Pythagorean identity. The next set are called the cofunction identities. And there are 6 of those, I believe, right? To prove this, what I'm going to do is just kind of show a graph for the first one, and then I'm not going to prove the rest of them because it's the exact same idea. So if I think about this, this is that, right? So if I look at just the sine part, I have an a value of 1, a b value of -1, an h value of pi over 2, and a k value of 0. I factored out a -1. Okay. If I factor out a -1, that becomes negative pi over 2 plus theta, right? And then if because it's addition, I can just write it in that, because that's still the same thing, right? Oops. Plus a negative, which is the same thing as subtraction. And the only reason I wanted to write that is so that this is in like the standard form when I go about trying to draw the graph here. Okay with that, Julia? Again, this is not something that I'd expect you to be able to repeat on a test or quiz. the derivations of these things. When we get down to actually using them, I'd actually expect to be able to use them to do things, but I don't want it to appear so much like magic as to what's going on. I want it to feel like this connects to ideas that we've done before. Is everybody happy so far? Relatively speaking, I know you're in math class, so you can't be that happy about it, but so I'm going to do my key points for sine. And if I transform them, I end up with pi over 2, 0, and then I have pi 1, oops, that's not that. That's 0. Egads! So if I graph this, I have pi over 2, 0, and 0, 1. I have negative pi over 2, 0. I have negative pi, negative 1. And I have negative 3 pi over 2, 0. And if I just kept extending this, the next one would be up here. And the next one here would be down here, and then there, and then there. And if I graph cosine on the same axis, if I go to the key points of cosine, they are 0, negative 1, pi over 2, 0, pi, negative 1, 3 pi over 2, 0, and 2 pi, 1. And what do you notice here the graph of cosine is? You guys notice anything there between the two graphs? They are the same. So what does that tell you about these two functions here? They're the same. Everybody's okay with that idea? So that's one of the 6. And to do the other 6, I would just do a similar proof, but God help me that I'm not going to do that 5 more times. Yes, but I will explain to you the form that we're going to use to do them, and now you're going to find that they're not maybe as bad as you think that they're going to be. So they turn into being things that are fairly manageable. So let's just finish the rest of these 3. So we have cosine pi over 2 minus theta is sine. We have tangent pi over 2 minus theta is cotangent. We have cotangent, pi over 2 minus theta is tangent. I'm sorry, what? They are opposite of what the sheet says. Oh. Okay. So this is still right, correct? It was just your... Well, is this is what you're talking about, right? Like, are these two things the same? Are those the same equations? This and this? Yes, right? Because, like, x equals 2 is the same thing as 2 equals x, right? Is this one the same? No, those are two different things. They're related to one another. Yeah, they don't mean the same thing, though. They are related. And again, like if you wanted to really shortcut some of this proof, you could do just work from one of them to the next one to the next one, but we're not going to do all of that, as it's in the interest of time mostly. And the last set that I want to talk about today are the odd-even identities. Did you guys talk about odd and even functions before I got here? Okay, well then we won't draw that analogy. The first one is that sine of negative x is equal to sine x. So remember when we talked about where sine and cosine were positive and negative? We said stuff like this, that where, like, cosine is positive in the first quadrant, negative in the second, negative in the third, and positive in the fourth. And then sine is positive in the first, positive in the second. Jeepers creepers. Forgot to draw that. Negative in the third and negative in the fourth, right? So if I have, say, sine theta here, this would be negative theta there, right? Everybody agree with that? When we make our triangle here, those triangles are going to have the same dimension, correct? Everybody agree there? The only difference is that the value for sine is positive in this quadrant, but negative in that quadrant, right? Everybody agree with that? So that's what this is kind of saying here, is if I take this value, sine of negative x, what I can do is find the value for sine of x and then make it negative, which would put me back down here again. So that's the first identity. Again, a little bit explanation-y rather than real formal proof, but for the course, that's okay. Again, these are things I would not expect you to be able to repeat for me. If I do the same thing with cosine, if I draw a negative, oops, we're supposed to be using thetas right now. Sorry, guys. Oh, good point. Thank you, Julia. So if I have cosine theta in the first quadrant, and I make it negative, it's still positive. I still have a positive value of cosine, right? So again, if I do like cosine of negative x, it's still going to be a positive value. It's going to be the same thing as the cosine in the first quadrant. Does everybody agree with that? So there's that. And then if you just take the first equation and divide it by the second equation, you have sine negative theta over cosine negative theta equals negative sine theta over cosine theta. And what is sine negative theta divided by cosine negative theta the same as? Tan negative theta. And what is negative sine over cosine going to be the same as? Negative tan theta. And similarly, we can kind of continue doing this. So I'm not going to prove the rest of them in the interest of time. And again, I wouldn't expect that you are would be able to reproduce these same arguments for me on a test or a quiz. But I think it's helpful to kind of see at least how we would go about doing that sort of thing.